a couple months ago. So it involves basically the Axion production in magnetars and then the subsequent Axion conversion to photons in the magnetar magnetosphere. My collaborators are Jeff Fortin at Laval University in Canada, Huike Guo at University of Oklahoma, Elijah Sheridan at Vanderbilt, and Kuver Sinha, also at Oklahoma. We also have a review article for the International Journal of Modern Physics D, which covers the topics that I discuss here, and also axions in neutron star mergers and Bose-Einstein condensates of axions and axion production in laboratory experiments. So that's a very good reference, I think. It has some additional collaborators. And of course, I want to point out this paper written by Jeff Fortin and Kuver Sinha, which goes into a lot of detail on the axion photon conversion process. So my talk can basically be outlined in a single picture, which is kind of nice. So you have a neutron star or a magnetar, and it has nuclear matter inside of it, and it produces axions. These axions weakly interact. I mean, they're not very strongly interacting, and so they escape the neutron star and enter the magnetosphere, and with some efficiency or some probability, convert into photons. And some of those photons we would happen to pick up if axions exist in our X-ray telescopes or in gamma ray telescopes. I will concentrate on the X-ray component. And that's basically the idea. The axion production is related to the axion neutron coupling. The axion photon conversion is related to the axion photon coupling. And so the number of photons we detect from this conversion process will somehow tell us the strength of the axion coupling to particles. And so I'll go through basically each step of this process in this talk. So axions are pseudoscalar bosons that were introduced to solve the strong CP problem. But we don't really need to know anything about their theoretical motivations. We all agree that they're very interesting particles. And so we're going to focus on kind of a generalization of the axion and called the axion-like particle, or the ALP, but I'll just refer to it as an axion. And this particle is defined just basically through its interactions with standard model particles. And that's really what we're going to try to probe here. So for example, the axion might couple to photons with this term and this coupling strength Ga gamma gamma. It could couple to electrons, but we don't actually care about this for this talk, so I'm not going to talk about that. And the axion could couple to neutrons or protons with some coupling strength capital G. We'll assume the coupling to neutrons and the coupling to protons are equal, just for simplicity. Because the axion couples to certain standard model particles, you can produce axions through a variety of processes, and I've listed some of them down below. And the ones that are relevant to us, I will get into more detail on later in this talk. So where are we producing the axions? It's in a neutron star or a magnetar. And so broadly speaking, if you zoom out, a neutron star is two parts. It has a crust region, which is just like a lattice of nuclei which are immersed in a Fermi sea of electrons. And it has a core region. So when you move in from the interior, in from the crust into the interior of the star, the nuclei get closer and closer together, and eventually they touch and merge into this new phase, which is a uniform Fermi liquid of neutrons, protons, and electrons. Most of the neutron star is this core region, and in fact, this core region is expected to dominate the axion production. So the only part of the neutron star I'm going to talk about today is the core. We'll ignore the crust entirely. Of course, at the very center of the star, you might have exotic phases of matter, like quark matter or hyperonic matter. We will also ignore those. And so basically, we're going to study several magnetars in this talk, and we will assume they're all 1.4 solar mass neutron stars with regular old neutron, proton, electron matter described by the IUF equation of state. And we'll assume some particular type of superfluidity, which I'll describe later. I'll also describe kind of what happens if we change the first two conditions a little bit. The answer is not much, but yeah, I'll get into that later in the talk. Okay, so you have neutron stars, and some of those neutron stars are magnetars. So what makes a star a magnetar? Here are two histograms of all of the neutron stars that we had observed as a community up until 2013, 2014. They're histogrammed on the left plot by their magnetic field at the surface of the star and by their age on the right plot. So you see that typical magnetic fields of neutron stars seem to kind of peak, like they're mostly around 10 to the 12 Gauss or so at their surface, but with some distribution around that value. Magnetars are the ones in red here. So they're at the very tail end of the spectrum. Their magnetic fields are very high at the surface, 10 to the 14 Gauss, maybe even 10 to the 15 Gauss. That's why they're called magnetars. Also, they're pretty young stars relative to the typical neutron star. The typical neutron star might be 10 to the 7 or 10 to the 6 years old. Magnetars seem to be more like 1,000 or 10,000 years old. But again, there's some distribution. Because these stars are fairly young, they're still at a pretty high temperature. They haven't had a long time to cool off via neutrino emission. So it's fair to assume that magnetars are pretty warm compared to most isolated neutron stars. So for a conventional neutron star, what you can do is you can look at its surface and the photon spectrum that's emitted from there and infer a black body temperature for the surface. And then it's actually, there's some agreed upon way to convert that into a core temperature based on like the thermal conductivity of inside of the neutron star and what material makes up the envelope separating the surface from the core. So typically, if you know the surface emission and the surface temperature, you can get the core temperature for a neutron star. But for a magnetar, this is not true. If you use this relationship, so you can look at a magnetar and measure its black body temperature at the surface, and you find it's pretty high. In fact, so high that if you use the typical core crust temperature relationship for neutron stars, you get back a core temperature that's so high that it's ridiculous. If it were actually that high, then it would emit a lot of neutrinos and quickly cool down from that temperature. So you wouldn't expect a 10,000-year-old star magnetar to have that high of a core temperature. So this is another way of saying that magnetars seem to violate this typical core crust temperature relationship. And we don't know what their core crust temperature relationship should be. It's expected that their high magnetic field kind of helps them violate this relationship. So long story short, we really don't know the core temperature of a magnetar very well, even though we know the surface temperature. So that's unfortunate. And that will be the biggest uncertainty in this entire talk, is the core temperature of the magnetar, because that affects the Axion production. But because magnetars are fairly young stars, we'll do what I think is a pretty common assumption, and that is to assume the core temperature is somewhere in the region of 10 to the 8th to 10 to the 9th Kelvin. And basically, whenever we get a result, it'll be as a function of the core temperature, which is unknown. Of course, it's possible that the magnetar core lies outside of this region, and our analysis would have to be adjusted in that case. Okay, so let's still continue to ignore superconductivity for a little bit, or superfluidity, and just pretend the nuclear matter in the neutron star is regular, uniform neutron, proton, electron matter, no spectral gaps or anything. In that case, how do you produce axions? Well, the answer is you produce them via these nucleon Bremsstrahlung processes, either neutron-neutron scattering to neutron-neutron axion, or proton-proton to proton-proton axion, or the mixed case neutron-proton to neutron-proton axion. This basically involves two nucleons interacting via the strong interaction, pushing one of them off shell, then it emits an axion to get back on shell. In cold nuclear matter, so we want to figure out like how often this production process happens, right? What energy is lost due to the creation of axions in the neutron star. This is called the emissivity. It's denoted by Q. And when the neutron star is strongly degenerate, which these magnetars would be expected to be, you can actually get an analytic expression for this energy loss, this emissivity, and it looks like this. So first of all, I should mention that we model the strong interaction by 1 pion exchange, but we know that's not a good approximation. It's been shown, it's off by about a factor of 4. It's a factor of 4 too large at saturation density or so. And so we insert this factor C here to kind of divide our result by 4, divide the 1 pion exchange result by 4. Otherwise, the emissivity is related to just two important quantities. There's the axion-neutron coupling constant, right? Of course, the axion emission rate depends on how strongly the axion couples to nucleons. And then there's temperature to the sixth power. This is why it's so important to know the magnetar core temperature, is because the axion emission rate depends on it to the sixth power. So it would be really great to know it, but we don't, unfortunately. Also, as part of this paper that we wrote, we did the first analytic degenerate calculation of this neutron-proton to neutron-proton axion production rate. It's a very complicated formula. I'm not going to show it here, but it's in our paper. Okay, so now what if the nuclear matter is superfluid? How do the axion production processes change? Well, first, let me talk a little bit about superfluidity or superconductivity. So why would we expect nuclear matter to be superfluid or superconducting? It's because of the Cooper theorem. Basically, what that says is that if you have a system of degenerate fermions and those fermions attract each other in a particular angular momentum channel and at a particular energy scale, if the interaction is attractive at that scale, then they can Cooper pair. And so you have to ask yourself, okay, nucleons in a neutron star interact via the strong interaction. So what is that? You have to know the nuclear force. And we only have a certain knowledge of that. It's not a complete knowledge. There's some error. And then once you know that nuclear force, or you choose your model of it, then you have to look at what energy scales and what angular momentum channels is it attractive in. And so that can be done. And what you find is this general expectation here in this plot. You find you would expect neutrons to pair in the singlet channel in the crust of the neutron star. But we don't care about the crust, so we're going to ignore that entirely. You would expect protons to pair in the singlet channel throughout most of the neutron star core. We will consider that. You would also expect the neutrons to pair in the triplet channel in the neutron star core, but that's a lot weaker of an effect, and it happens at lower temperatures. So we're also going to ignore that under the assumption that magnetars have a fairly high temperature. So superconductivity or superfluidity is a phenomenon that happens below some critical temperature. So if you have very cold matter and the proper conditions for attractive interactions, et cetera, then you'll be in the superfluid phase. But as you increase the temperature, eventually you'll pass a critical temperature and your matter will no longer be superfluid or Cooper paired. You can take some constraints from neutron star cooling and learn that in this, if the neutron star is kind of in this temperature range, then you would expect proton pairing in the singlet channel, and you would not really expect neutron pairing in the triplet channel. So this is all just to say, we'll consider 1s0 or singlet proton pairing in the neutron star core, according to some model that we choose. We choose what is called the CCDK model. Basically what that means is that it gives us a critical temperature profile throughout the canonical 1.4 solar mass neutron star that we're looking at. This is just one model. It's not to say it's the correct model, but it at least obeys certain constraints that have been put on it. And what the model says is that at the very center of the neutron star, the critical temperature, remember below the critical temperature is where you have the proton Cooper pairing. That critical temperature is like 10 to the 9th Kelvin in the core. And as you move out to the edge of the star, right before you hit the crust, the critical temperature is a lot higher. It's 6 or 7 times that. From this, you can get the gap in the proton energy spectrum, which I'll talk a little bit about later. It's plotted here. I guess that's all I really have to say about that. It's a few hundred keV, and it depends on the position inside of the star because it depends on the density. Okay, now why do we care about this whole superfluidity thing or superconducting protons thing? It's because of the gap in the energy spectrum that happens when you have Cooper pairing. So because the gap only happens at the Fermi surface, the bulk properties of the neutron star are not affected by it because there are only few particles at the Fermi surface. Most of them are below the Fermi surface in the Fermi sea somewhere. However, anything that involves transport or low energy excitations around the Fermi surface, that stuff is killed by superconductivity. It's suppressed by e to the minus the gap, a few hundred keV, over the temperature. And if the temperature is very cold, then that suppression is enormous. So for example, the axion production rate, the rate of this Bremsstrahlung scattering process that produces axions, it is actually suppressed by e to the minus gap over the temperature if the protons are paired in that particular region of the neutron star at that particular temperature. So you would think, okay, the axion production is just suppressed by superfluidity or superconductivity. But actually, that's not necessarily true because you get a new axion production process. So when your protons are in the superfluid phase, not all of them are paired. Only some of them are paired. And the ratio between paired protons and unpaired protons is a function of the temperature that your system is at in relation to the critical temperature. And so constantly protons are pairing and unpairing. And when they pair, you can produce an axion. And that axion can take away 2 delta, where delta is the gap of energy, because 2 delta is the binding energy of the Cooper pair. So in superfluid matter, your Bremsstrahlung rates are suppressed, but you get this new Cooper pair formation process that can also produce axions. However, these axions have a minimum energy that's 2 delta. And actually, that will be the reason that we don't care about them for this particular project. So we don't care about the Cooper pair breaking process for this project, but I'm still going to just describe it for context, I suppose. Okay, so you can look at the emissivity of axions. Remember, this is sensitive to the axion-neutron coupling constant, which is why we are still talking about it. So here is the axion luminosity as a function of temperature of the core. We assume the core of the magnetar is isothermal. So at low temperatures, so when you're very much in the superfluid phase, only the neutron Bremsstrahlung process, the black curve here, clearly dominates. And that's because any process involving protons is just killed by the superfluidity. It's that e to the minus gap over the temperature factor that I was talking about before. As you increase the temperature, that e to the minus delta over t becomes less and less of a suppression factor. And when you get up to 10 to the 9th Kelvin or so, or maybe even a little bit higher than that, there's really no suppression of proton involving processes anymore. Pretty much all the Bremsstrahlung processes are important. The blue curve is the Cooper pair breaking process, which does contribute to axion emission. It's just we don't care about those axions that it does emit for reasons I'll explain in the next plot. But once you get to a very high temperature, well above what we expect these magnetars to be, the protons are no longer Cooper paired, and so that production rate from Cooper pair breaking just drops to 0. And that's pretty clear where that happens. Okay, here on the right plot is the spectrum of the axions that are emitted. Let's just look at 5 times 10 to the 8th Kelvin. So that's this curve here where I'm moving my mouse. The black curve is the Bremsstrahlung contribution to the axion spectrum. And that peaks at around twice the temperature in terms of the energy of the axion it produces. So it can produce low energy axions, whereas the Cooper pair breaking process can't. It produces them at a minimum energy of like 300 keV. And that's because they're cut off by the gap. You can't produce an axion that has an energy of less than twice the gap. And that's the minimum value of the gap in the magnetars, 150 keV times 2, because it's 2 delta. Now, we want to do axion photon conversion, which I'm about to get to. And energy is conserved when axions convert into photons. And we only care about hard X-ray photons, which are in the 20 keV to 150 keV range. And so we only care about axion energies that are in that 20 keV to 150 keV range. So that's only the very leftmost portion of this plot. And so only the Bremsstrahlung process produces axions that are in that energy range that can then convert to hard X-rays that we can see in our telescopes. So in this project, even though I talked about Cooper pair breaking to produce axions, we only care about Bremsstrahlung that produces axions. Okay, let me talk about axion photon conversion. So this is sensitive to the axion photon coupling, which is why we care about it. And basically, this term in the Lagrangian, this type of coupling, allows the photons to convert into axions as long as you're in a magnetic field, which you are in a magnetosphere of a magnetar. You get this mixing between axion and photon terms that is just like neutrino oscillations. Just a note, we include strong magnetic field corrections in our Lagrangian. And so you can basically, just like in neutrino oscillations, track basically the state in this 3-component vector. If you're an axion, or if you're one component of the electric field, or if you're another component of the electric field, and yeah, that propagates as a function of time or distance away from the magnetar according to this mixing matrix. You'll see that one component decouples, so because it's diagonal, so we don't care about the perpendicular component of the electric field, just the parallel and then the axion. You see there are diagonal terms and there are off-diagonal terms. The diagonal terms don't affect mixing at all. So they will not help you convert axions into photons, but the off-diagonal terms will. So this delta M term is basically how well you can convert axions into photons, how readily you can do that. And you'll see that delta M here is related to the axion photon coupling, so that makes perfect sense, and also the magnetic field. And so a strong magnetic field means lots of mixing, which is good. what you really want is you want the mixing to be strong compared to what the diagonal term is. And so you can plot basically the diagonal terms versus the mixing term as a function of how far away from the neutron star you are. So right at the surface, this left part of the plot, this was studied by Rafelt and Sadolsky back in 1988 when they first did this Axion photon conversion business. And what they found is that the diagonal terms are very big and the mixing is very small. And so they said, okay, well, it doesn't seem like you can have Axion photon conversion that happens with any reasonable efficiency. But what Jeff Fortin and Kuver Sinha did a couple decades later was to look farther away from the neutron star. And they found that right around 1,000 times the distance, times the radius away from the neutron star, you get the mixing is actually dominant, or at least close to dominant. And so you can get a lot of Axion photon conversion at that point, and then very little afterwards. The typical probabilities we're talking about here are shown in the right plot here. They're functions of the Axion energy and various couplings, but maybe 1% or maybe 10% conversion efficiency. So what we do is then we basically want to figure out how many photons in an energy bin that we might see from a magnetar could come from axions. So we take the number of axions that are created, weighted by their energy, and then times the probability that that given axion converts into a photon. And we average that over all the angles that are involved. And this is some quantity that's proportional to the coupling strengths, right? The axion-neutron coupling because of axion production, and the axion-photon coupling because of axion-photon conversion, squared, it happens. And we demand that in each energy bin, the photons that come from axions are less than the photons we actually observed in that energy bin from that magnetar, right? That's the most conservative estimate we can do. Obviously, you can't have more photons that come from axions than you actually observed. So this allows you to set an upper bound on the product of these coupling constants. And so that's what we show here in this right plot. Of course, this bound is entirely a function of temperature of the core of the magnetar, which we don't know. So we show 4 different core temperatures here. I'm sorry, they're not labeled, but a low core temperature are these 2 curves up here in pink, because you can't, if you're not expected to produce many axions from this whole process, then because you have a low temperature, then you can't constrain them very well. But if you were expected, so the bottom curve here is at the highest possible magnetar core temperature. This would say, okay, you have a high magnetar core temperature, you expect to produce a lot of axions there. And so you're able to constrain them quite well if the magnetar were to be at this core temperature. I'll overlay this plot on plots of other constraints of this GA and GA gamma gamma plot in a subsequent slide. I will say that maybe you have a high magnetic field so high inside the magnetar that it actually destroys proton superconductivity. That could happen. And so the solid curves are basically what would happen in that case, where you don't have any superconductivity at all. Okay, let me just kind of dispel the other uncertainties that you might think would be important. If you vary the magnetar mass, this ends up, so it's not necessarily 1.4 solar masses, because we don't actually know the mass of the magnetar. This leads to less than a factor of 2 correction in the production rate. Varying the equation of state is also less than a factor of 2 correction. Doing different models of the proton superfluidity, that's also less than a factor of 2 correction, because the neutrons are still not superfluid, and so that dominates the production. Of course, if the neutrons were superfluid, then the production rate would drop dramatically. So combining all of these uncertainties, the mass, the equation of state, the superfluidity together, you get less than a factor of 3 correction, from the results that I've shown before in the axion production rate spectrum. So that just leaves, are the neutrons superfluid and superfluid, or what's the core temperature? Those are the 2 big uncertainties we have. To put our results into context, the hard X-ray results I've shown here from magnetars, assuming 10 to the 9th Kelvin is this curve I'm kind of moving my mouse over right now, this blue curve. If you reduce the core temperature to 5 times 10 to the 8th Kelvin, you get this blue dotted curve here. You can do a very similar analysis for soft gamma rays. You get the pink curves. And then I know like Ben Safdie and his group did analysis of the Magnificent 7, which are just conventional neutron stars, not magnetars. They get this result here. And then if you just take the separately the coupling constraints on axion neutron from supernova 1987A and the axion photon constraint from CAST and multiply them together, you get this gray shaded region here. So our point here is, yes, we don't know the core temperature, but for reasonable values of the core temperature, our constraints are quite competitive with the other constraints that are in the ballgame here. So to conclude, magnetars emit axions, and that production rate is related to the axion-nucleon coupling constant squared. Those axions convert into photons in the magnetosphere, and that's related to the axion-photon coupling squared. And then we measure the hard X-ray photons from the magnetars and demand that the theoretical number of axions that are produced, of photons that are produced from axions ultimately is less than the number of photons per energy bin that we observed actually from those magnetars for each magnetar that we look at. And then our results happen to be quite competitive with the existing results. And let me just say, magnetars, they're good to look at because they have a high temperature. So they produce a lot of axions and a high magnetic field. So those axions are quite likely, relatively speaking, to convert into photons. One last slide. Future prospects. There's lots of work still to be done in this general area of axions from magnetars. So it's absolutely vital we better understand the core crust temperature relationship in magnetars. That's almost the entire cause of our uncertainty in the axion coupling constraints. It would be great to incorporate a more sophisticated model of the magnetar magnetosphere. See this paper by Matthew Baring et al. Studying the effects of a non-dipolar magnetic field. We assumed our magnetic field outside of the neutron star was dipolar because that's what the textbook would say, right? It's the most conventional thing. But NICER has shown some results that show definitely near the neutron star surface, the magnetic field is not dipolar, and perhaps farther away from the surface, it would also deviate. I don't know. There are also ways the magnetic field can drive additional axion production processes. We did not consider that, but this paper does. It goes through some examples of those processes. I've ignored neutron triplet pairing, but if we were to actually know the critical temperature of that and find that it was 2 × 10⁸ Kelvin, let's say, then we would have to include that in our analysis. Of course, there could be exotic phases inside of the very densest regions of a neutron star. We ignored those, but it would be great to include them. And finally, there's been a lot of recent work in looking at the axion in the context of dense matter and seeing how its actual properties change when it's in dense matter. And that's done in this paper here. For example, you see that the axion-nucleon coupling constant is actually a function of density, which is not at all something we've considered. So lots of future work. This is a very exciting field. Thank you very much.
Thanks a lot, Stephen. So you have questions. The first question is from Chris Desert. He asks, have you thought about using measurements of the age of these magnetars, either by their surface temperatures or by kinematic measurements, in tandem with a neutron star cooling model to get a better constraint on the core temperatures?
Yes. Yeah, so we can get, see the problem here is still that for magnetars, I don't think we really understand how the heat is transferred from the crust to the core. We think the magnetic field actually changes this because it's so strong in compared to a regular old neutron star with a weaker magnetic field. And so this quite complicates the analysis, but we're pretty sure the magnetic field is why the surface temperature is so hot. But there have been a number of possible proposed mechanisms for this magnetic field turning into crustal heat phenomenon. And yes, I think it would be great to further explore that.
Makes a lot of sense.
Okay, so George has his hand raised. George, you can go.
Thank you. A very interesting talk. Could you show the slide just previous to your conclusion slide, that maybe is slide 15?
This one?
Yeah. So I'm just trying to understand the role, if any, of the conversion probability. Mm-hmm. If I put my neutrino oscillation hat on, which I have on frequently, I would say that this looks, as you pointed out, very similar to medium enhanced neutrino flavor transformation at MSW. And so there I would look for something like a resonance roughly when the plasma frequency of some electromagnetic mode, i.e. a photon, is about the same as the axion mass.
Right.
So I'm seeing a large range of mass in this figure, 5 orders of magnitude or more. And so that tells me that you could get resonances at very different places. And you, in your talk, you singled out I think the location for most of the conversion at something like 1,000, hundreds or 1,000 or so neutron star radius. Is that right?
Yeah, that's right.
So I'm trying to fit all that together. Is that roughly where the plasma frequency is comparable to, some mass on this horizontal scale here?
Yeah. So I have to admit, this is not the part of the talk that I'm really an expert in. But I think Coover is here, my collaborator, so maybe he can say a little bit more after I say one thing. My understanding is that, so for radio frequency axion, for axions propagating in radio frequencies, that's when you have a lot of the plasma effects that happen. But and they're not that prominent for axions with higher energies. But yeah, I don't know. Maybe if Coover is here, maybe he could say something.
Sure. Stephen, if you could scroll back to the slide that showed the conversion probability. Yeah, right there. So, right. So the competition here is between the diagonal term delta parallel in red,
sure,
which is actually
exactly like in the neutrino oscillation problem.
That's right. Yeah. So that's the Euler Heisenberg sort of induced mass of the photon, and then you have the off diagonal couplings G gamma gamma times B. So so if you look at the off diagonal terms, they go as 1 over r cube because B is dipolar. The Euler Heisenberg term on the diagonal goes as 1 over r to the 6 because the photon mass goes as B squared. At around r equals 1000, r cube becomes order r to the 6.
Hang on one second, though. When you say the photon effective mass goes like the magnetic field, doesn't it also depend on electron number density? Or maybe it doesn't because the frequency is so high here?
That's right, yes. If you were doing radio waves with cold axions, which Chris has written on, there the actual plasma frequency would be a very important factor. And in fact, you really have to be careful about modeling that. But for X-rays, it's much cleaner. You really the plasma frequency really decouples from the entire game.
Okay, thank you. That answers my question in part. But also, even if I just ignore the in medium corrections to the photon effective mass,
yes,
you can still get a level crossing here when the frequency of the photon mode is equal to capital delta sub A.
Oh, right. Okay, so if you look at the range of axion masses, so delta A relates to the range of axion masses divided by the hard X-ray frequency, omega. If you look at the range of axion masses that we are interested in, yeah, so this is the kind of effect that you get.
Yeah, that's what I was asking about. That's a large range in mass.
That's right. So because the mass of the axion is unknown and we want to cover a large range of masses, once MA becomes very large, order 10 to the minus 3 or 10 to the minus 4, that diagonal term dominates over everything in the game and you're just gone. There's no mixing anymore. Okay, so the delta A at that point becomes larger than everything in the game. But if delta is very small, then it also decouples. It sort of doesn't play a role anymore. So then the competition really just becomes between delta M and delta parallel. Now, if you're in that regime where the curves are sort of going up, then all three are in the game. And then you have to do, of course, our results do a full sort of numerical calculation of this probability conversion. And so then all the three factors have to be taken into account carefully.
Good, thank you. That answers my question.
All right.
Okay, Shashank has a question. Shashank, you can go ahead.
Yeah, so my question is regarding the large magnetic fields that are present in magnetars. So my general question was kind of related to what George was saying, that when you have such large magnetic fields, non-linearities can creep in. I just was thinking about the Schwinger limit, but there could be other non-linear effects which creep into the system. And my question was whether there can be nonlinear correction to either the axion production or the axion to photon conversion like processes. Will they have any nonlinear correction due to the large magnetic field?
So maybe Stephen, I can
Sure.
take the conversion part and you can take the production part.
Yeah, go ahead.
So for the conversion part, you're absolutely right. The Euler-Heisenberg Lagrangian is, of course, an expansion in powers of various things, including the magnetic field and the energy. So if you really wanted to be fully careful, you would have to include the entire photon axion Lagrangian in the full Schwinger limit. Now, if you remember the way we go from the full Lagrangian to the Euler-Heisenberg Lagrangian, there are powers of energy over the mass of the electron, right? So now, because we're in the range of 20 to 150 keV, we can actually stop the perturbation at the level where we can actually approximate it with the Euler-Heisenberg Lagrangian, just because, again, if you go up to 500 keV or more, or 1 MeV, then you have to be slightly more careful. One can also do a similar thing for the magnetic field, and we actually discuss all of these in our IJMPD review in one of the appendices. So we actually cover all these expansions in one of those appendices.
Thanks, Cooper. Yeah, as for the production part, I genuinely do not know much about the effect of high magnetic fields on processes like the Bremsstrahlung process. Typically, it's just assumed that they don't have much of an effect until you get to really high magnetic fields, like 10 to the 17th Gauss or something like that, which is not really expected. But it's something I need to look more into, and I want to. That's kind of why I included it as a future, well, kind of implicitly in my future prospects, just like, yeah, magnetic field driven axion production processes. I think there are a couple of good review papers, but I don't think this one that I listed here talks about it very much, unfortunately. Yeah.
Okay, thank you very much.
Okay, I think there is another comment from Zorawar. You can go ahead. Can you unmute and go ahead?
Yes. I guess it's a menagerie of comments I have in the chat. It's so the pure dipole field is formally unstable. You typically require a small toroidal component, equatorial component, to stabilize the magnetic field. So I think the dipole approximation is probably secure unless something strange is going on. The hard X-ray in magnetars is highly pulsed. I don't think the axion signal would be, right? So it has to contend with this astrophysical contamination.
Mm-hmm.
And the third comment is the QED birefringence from the nonlinear effects. The index of refraction in pure QED, I guess, not including any axion physics, it differs from unity at sort of the 10 to the minus 2 times the quantum critical field squared. So it's not important, at least in the magnetosphere, unless you're very, very, very close to the surface.
So, Stephen, do you want me to take that?
Yeah, you can address the last one. Yeah.
Okay, so about the hard X-ray emission, I think that's by the way, we learned a lot from your papers with Matthew and Alice. So you're right, the axion emission is not pulsed. In order to actually claim anything over astrophysics, we would have to do astrophysical background modeling, which is a whole separate game in which you guys are the experts. And so then you'd have to do actual signal over background modeling to claim any kind of excess and claim a discovery of axions. That we can't do at this stage. What we're doing is something much more conservative. We're just saying we have our theory model, we compare it to observed hard X-rays, and we just say, well, theory can't be more than what we actually observe. what we observe may be completely astrophysical, but at least we have some constraints on axions. And for the last one, for the nonlinear QED effects, it is true that the index of refraction is different from unity at the level of it's a small number. But it turns out that small, in fact, that's probably why Rafut and Studolsky did not, consider it away from the surface. But it is a small, you have to also remember that these axion photon couplings are also very small numbers. So there are two small numbers that are contending with each other. And at order 1,000 times the radius of the neutron star, the two small numbers, one on the diagonal and one on the off diagonal, become order each other, and the mixing angle becomes substantial. So that's sort of what's going on there.
Okay.
Okay, are there any more questions? If not, let us thank Stephen again, and we'll meet again in a couple of weeks. Thank you, Stephen.
Thanks, guys.
Thank you.